Let's think about cause and effect on the space-time diagram. So let's say that I am located at this value of x, and at this moment in time, I throw an object to the right. So event A corresponds to me throwing an object to the right. And let's say that you're sitting at this x value, and eventually you catch this object. Now I have to throw this object slower than the speed of light, and the speed of light travels on a 45-degree line. So the speed of light to the right looks like this on the space-time diagram. So this is c. And so I have to launch the object. Let's say the object moves at a constant speed, and so it will reach this location. Right, this is light reaching that location where you are, and so it's going to take a longer time, t, to reach you. So let's say it reaches you at that moment in time. So that's event B, you catching the object that I throw to you. And so we need to make a line. If that's a straight line, it represents the object moving to the right at constant speed, slower than the speed of light. Okay, so there's a cause and effect relationship there. It's clear that TA is less than TB, right? Event A happens before event B. Let's see that that's the case for all observers. So is causality preserved? Is the cause and effect relationship preserved from the perspective of a moving observer? So let's say that we have a moving observer, and so we have T bar. Not the greatest drawing. The axes seem to tilt differently here and there, but that's sort of T bar, and X bar then would have to be something like that. This is X bar. Does something like that. Let's see the time coordinates according to the moving observer. So event A, here's event A, and we need to travel along the X bar direction to get to the time axis. So we're moving along a line that's parallel to that, and so we're going to move something like that to get the time. There's the time T A bar. And we'll do the same thing for event B, traveling parallel to this. So that's going to be something like that. And so we can clearly see that T B bar is also greater than T A bar. Right, so it's true that the cause and effect relationship is preserved regardless of the motion of the observer. Maybe we can try to think about this if we make the moving observer moving faster and faster. So let's see if we can do this. Maybe we'll make another diagram here. So here's event A, and I'm going to have event B up here. So we'll connect these two with a line that's smaller than 45 degrees. That's the throwing and the catching on the space-time diagram. Let's look at this from the perspective of an observer that's moving very close to the speed of light. So the t-bar and x-bar axis sort of close in on each other, and they approach the 45-degree line. Now, they can't really be 45 degrees. They have to be a little bit less. But that's t-bar. So I'm tilting a little bit more to the t. I'm tilting a little bit more to this. I can do that, something like that. And the x bar axis is close to the t-bar axis. I guess I won't draw it. Let's see if we can ensure the cause and effect relationship from the perspective of this moving observer. So I have to travel parallel to x bar axes. The x bar axes are close to being the t bar axis, but they're a little bit more tilted to the x. So I'm going to be moving a little bit towards, and will eventually hit the blue axis, the t-bar axis. I won't be moving exactly parallel, but it'll take me a while to get there. So I have to travel something like that, and eventually I'll hit the t-bar axis down there somewhere. The same is true of this, but I can see that by virtue of the locations of A and B, that if both of these bend in the same way, right, the B event will hit somewhere there, whereas the A event will hit somewhere down there. And I'll always have, therefore, that T bar B is greater than T bar A. And that way we can see that a physical process with a clear cause and effect relationship is preserved on the space-time diagram.